wire, right, and connect them. What I'm going to do right here actually is I am going to hook up. What I'm going to do is hook up one wire here. I'm going to hook up another wire, which is red.
Right there.
No, it's the clippy clip. Oh, sweet.
Oh.
All right.
I was like, Pratt.
Now, hopefully, maybe back from freshman year or something of the like. If I connect it right here, I'll do it here. So, right. If we think back to circuits and things like that, would I have any electrons moving like right now?
No.
Why?
Because it's an open.
Open circuit, because where do you see the open in the open circuit?
There.
Right? There's no connection here, right? And so what we need to have happen, right, is we actually need to have something where if electrons, say, are transferred from the zinc through the wire to the copper, right, what's going to happen, right, is this will lose electrons, this will gain electrons, and so what you're going to have is a misbalance of electrons. So what will happen is the electrons will transfer and whoop, and it's done, and there's no flow, right? So you need to add something that basically will add, so this is 1 molar potassium nitrate, so KNO3. What I've done is I've just soaked paper with it. You don't even need something this exact. This morning I just laid a piece of paper that was soaked in this between the two. And what that will do, I'm hoping this won't like leak everywhere. I'm hoping it'll kind of stay.
It's too fast. Oh, okay.
There we go. So what I'm going to do, hopefully that's enough to get it to work. Okay, so what we're doing now is that with the salt bridge here, what that will allow is that as electrons are gained by the copper, right, this is going to become more negative. So to help balance out the charge, the potassium will go in here to balance that out. Same thing here, right? As this starts to become more positive, the nitrate or the NO3 will come in here. And basically, it's trying to keep the charge balanced. That's all that this does. And by doing that, it allows the circuit to flow. Now, we can measure the circuit using this voltmeter. So we'll do a lab where you'll see these maybe around your house. You've seen one of these. You can test to see if circuits are working. Right, when I was doing electrical work in my house, I could use these. It's like $5 at Harbor Freight, really cheap. So what we're going to do is I'm going to take these two electrodes now, and I'm going to hook them up to our thing right here and see if this registers any current. Right. So right now we have a charge, and this is in volts. So we have 1.03 volts right now. How much is a car battery?
100.
No.
120.
It's only 12 volts in a car battery. But the reason there's so much electricity produced, there's this coil, it's called the condenser coil. It runs the charge through, and that like increases the voltage. So this is about a 1.02 volt cell. So in a car battery, one of the reasons why it's so heavy, they use lead in it, but what they essentially do is they'll have a cell like this, but since this is only 1 volt, right, if I hook up another cell of the same thing next to it and hook it all up, what do you think this will read? 2. And if I hook up a third one, 3, 4. So what they do is they hook up numerous of these cells together, and that creates essentially a 12-volt battery, right? One reaction, I think the greatest voltage you could have is maybe 2.5 or 3 volts between two different solutions. So if you want anything above that, you have to hook them up in series or connect them together. So this is at 1.20 volts right now. So that means there's electrons, right, that are leaving 1. And I think I had to check the book. I think the zinc gets oxidized. So what that means, right, is that the zinc, this is zinc metal, and it's being oxidized. So that means it's going from zinc 0 to zinc 2+. Okay? If it's turning into an ion, what does that mean? And it's going from a solid to what state?
Aqueous.
Aqueous, right? So if it's going from solid to aqueous, that means my zinc is slowly doing what? Dissolving, right? And so if I was to leave this here, right, for a period of time, you would actually start to see this start to get smaller and smaller. If we can't see it, we could take it, hook it up for an hour, then stick it on a scale, and we should see that the mass does what? Decreases, right? And so we're going to do a lab like that where you actually see the increase versus the decrease, and you can calculate moles and current and all that stuff. So if that's happening there, right, and this is being oxidized, then the converse is that this would be being reduced, and that would be copper 2+ turning into copper 0. So that rather than the solid going into solution, the solution would be going onto the solid, right? Because every redox reaction, there's an oxidation and there's a reduction. So one thing's dissolving while the other one's actually gaining mass, right? And it's proportional to moles. It's kind of a cool thing. So this is essentially what a cell is. And so what we can do is figure out, okay, how much voltage is released when this is oxidized versus this reduced. And when it adds up, that total voltage is what you read right here. Okay, so there's charts that scientists have done where we can just look at zinc. And what they do is they compare it to a standard electrode. So they chose one element to be like the standard, and they based everything from that. The element they chose is hydrogen. The only problem is hydrogen is a gas, right? So it's kind of hard to make a solution of. So what they do is they look at, they can use a platinum electrode. So it's this weird thing where it's like one of these where it's platinum, like it's an actual platinum metal, and it's in a glass container because there's gas in it. And so as the gas reacts and they bubble gas into it, as that, they compare that to zinc, and whatever that charge is, they'll say that's the charge for zinc. So they just use hydrogen as the base, and that's where all these voltages come from. And then when you add them up, that's what the number we'll get here. So really, what we're going to learn about is you're just doing addition, right? How much volts is released when this is reduced versus this is oxidized when you add them together? That's your voltage for your cell. Now, the cool thing about this, right, is that it's actually kind of accurate. So this is at 1 volt. I've had it more accurate before. When we do the calculation in the book, I think it's 1.09. So it's only about 9 hundredths off. So electrochemistry is relatively accurate, which is nice that it actually works. The fun thing you can do is that you can actually keep the circuit going. So I'm going to separate these, right? And if you hold on to them, right, you can still see, I don't know if you'll see this, right? So when you separate it, right, there's no voltage. Oh, yeah. Display to the class. Okay? When you touch them, right, it goes back up to 1. But if I use myself as a conductor in between, right, there's still a reading, right? All right, so now I'm going to, okay, Paulo, hold this.
Oh, wait, you guys should hold hands and, like, see.
Yeah, hold this over.
Yeah, and then see how.
What are we up to?
Oh, it's actually more. 0.4.
0.4.
0.42. Okay. Wait, by that logic, if we have, like, everyone hold hands, it should be, like, 14 volts.
Almost up there. Right? Let's try this. Okay, so y'all hold hands.
Wait.
Circle up.
Right?
Give that to Kit.
No, I'll hold this up, guys. I'll hold this up.
Okay, so Kit will be our holder.
Right?
You gotta give. Everyone hold hands.
No. I can't because I'm, like, holding.
No. So he's going to be out of it.
Oh.
Okay. So somebody's got to hold hands with Paulo. Aw. Okay. And then we got to keep going all the way across.
Outside.
Okay. Yep. There. Around. Okay. And then what I'm going to do. Okay. Is it 0?
Yeah, it's 0.
Okay. I'm going to touch this, and hopefully it should.
Touch it. Babe, you're not touching it.
You're not touching it. 22, 23.
And it's 0.4. Oh.
Oh, went down. Stop letting go.
Yeah, it's 0.4.
0.4. Okay, I'm going to let go.
0.45. 0.45.
I'm gonna increase my chocolate.
Everybody flex.
Oh. So there's actually a limit.
Electrons.
Okay.
In your body.
Yeah. So there's a limit.
Okay. And then I'll let go. Should go down to 0.
Yep.
Yeah.
Okay. Let's do this. Shen and Mason let go. See if it goes down to 0.
Yeah, 0.
I'm going to 0. Okay. Connect again. Yeah. Crazy, right? That there's actually small
Wait,
amounts
technically, we're all electrocuting each other. Think about it.
All right. We'll all flex our muscles. See if that does anything. 1, 2, 3. Flex.
Oh! It's higher! It's higher!
Nice.
Yeah, it was actually higher. Wow.
Okay. Let's try another one. All right. Everybody hold hands again. This is fun. Think of
1 to
something
5.5.
really, really sad, like puppies being beat with a bat.
Oh my gosh.
Why's it going?
It's going up.
Oh, it's going up so high.
1 to 0.5.
Rub each other's hand. I want to see that.
Do what?
Rub.
Rubbing hands, but if we can't let contact go. So.
Yeah. It's less.
Oh, it's last. Oh.
Don't let go.
Bet you it's the circle.
It's like, okay, 0.23. Okay.
So anyway, one other thing that is interesting about this, so there is a difference, we'll talk about this, between voltage and amps. I don't know if you've ever heard this, but voltage is actually potential. So you have very, very little current, So this is more physics, but current is measured in amps. That's how much electricity is flowing. That's not what this is measuring right now. This is measuring voltage, which is like how much potential could go through your body. And so the potential breaks when the circuit breaks, and so that's what we're measuring.
I was up to 68, bro. What's up?
Good time. Good time. All right. Cool. So what we're going to do is kind of diagram what's happening here. I'm going to leave this set up right here, so don't drink or do anything with these fluids. But y'all go back to your desks, and we'll
Hey,
kind of talk
what are
about
you suggesting?